Thank you, thank you. I hope that this is working, the microphone. I touched this wrong. What is the matter here? No, there it's up there. Okay. This lecture, all the stuff is on videos and GIFs on these two websites. Well, there's a couple of them that aren't on yet, but they'll be on there. So you can, if I say something and you didn't quite get it, you can look at this website and look through it and see more about it. It's the Google sites, so you got the site's google.com site, and then the name, and one is lessons on the internet and lessons on distributed computing. And they kind of go together. I guess the internet parts, that's the computer science part. The distributed computing, that's the MIS part of the subject matter. Okay, let's go to the other one. I start with Shannon. When I took the Ph.D., you walk in and they start talking about Shannon. Shannon for the internet is kind of like Turing for the computers. He was kind of the beginner of the whole thing. And he worked for the AT&T, and he was developing what we'd call internet type of connectivity for phone service long before anybody else knew what that was. And the old phone service, when you picked up the phone and dialed, you were connected physically to the person at the other end. I mean, it was wonderful, but you get so many phones and it doesn't work anymore. And Shannon knew that, so you developed this, what they call connectionless connection. You're not really connected to the other person. You're sending packets back and forth between you and that person, and most of the time you get the right packets. I've been on the phone and I'm hearing somebody else, but usually you get the right packets. And this was, the whole idea of doing that was developed by Shannon for the telephone company. Okay. And that's the calling, sending a message electronically. He developed the theory behind this. When you send a message electronically, you got to have some kind of change in the signal that's detected at the other end. And that's sort of a bit. And then you need a whole bunch of bits to say anything. So if you have one bit, you can say two things, and that's always with the computer, it's yes or no. You only have two options when you have one bit. When you have 2 bits, you have 4 options. When you have 3 bits, you have 8 options. And it's a powers of 2 type thing. The number of bits you have, you take 2 to that power, and that's the number of combinations you are available. So 4 bits, it's 16, and 5 bits is 32, 6 bits is 64. Well, in a computer, you have thousands and thousands of bits, and you can choose the number you want for your message, in a sense. In the development of coding in the early days, a lot of your bytes of the computer, what you grabbed at one time, were 8 bits. But one of those was a parity bit. So they developed their coding in the original on 7 bits. And because they couldn't use the other bit. Anymore, that's not true. They don't do what they called parity checking. They don't do parity checking. They have another way to check whether there's errors in a message than parity check. And so they don't waste a bit. It's wasting memory somewhere else where they do it. So you end up with 7 bits that are 1 or 0, and then you can make up your codes from that. That leaves 128 combinations, which they develop where they develop the ASCII code. There's competing codes. Some computers use AFCEA, but most today are using the ASCII code for the bits. So this is the 7-bit ASCII code and a table of all the codes that are possible. And this is what Shannon didn't invent ASCII, but he invented the concept of how many combinations you had available from so many bits, and then people decided what the combination would be. I mean, there were people that said, oh no, I can decide which code is which. Only there's certain rules for programmers, so like the alphabet is all in order, numbers are all in order, so you can add 1 to an A and make it a B, and programmers like to do stuff like that. So they set aside the first bunch for signals. These are signals that are going on in the computer, and they send bits to send that signal under certain circumstances. I gotta hold this way when I do it. Then they have some special characters. And then they get into the numbers and the capital letters with some other characters filled in, and then you have the small letters. Another thing, well, let's look at when you're sending information on the internet, it's just a line of data going across the wire, 1 0 1 0 1 0 whatever, and it's just going across the wire like that. And when we talk about where the data is, we don't talk about it this way because this means nothing to us. If you sat and said, well, this is what a packet looks like, and you did it in a line like that, now some programmers like to do this, is change it to hexadecimal, and it's a little more readable than the 1 0 1 0 1 0. That still doesn't help you when you're talking about a packet on the internet. So even though that's the way it's sent, is 1 0 1 0 1 0, we talk about it this way. It's a packet. And then such and such is here, such and such is here. This is the message, and this is some kind of an error check. And they actually look like this on the internet, but we do it this way because then in this batch, there's sort of a beginning of the packet, then the certain things in this part of the packet belong in certain places. They belong in certain places in that line. The computer can interpret it from the line. We can't. And we look at that line and it's just gibberish. So we always talk about that the packet's going over the internet, not the 1 0 1 0 1 0 1 0. Each of these they call protocol items, and they have certain information in them that's important that this packet is handled correctly. The thing is, this is what you're sending. This can't take too much room, this and this. It's got to be small, relatively speaking. So otherwise you'd waste a lot of stuff in the extras. But there's also a certain amount of information that has to be there, so they have to set aside that space. Now, one of the things that Shannon did is theories of how to encrypt. Now, he didn't invent all these encryption methods, but he taught people how to do encryption of data. And this was the original way of encrypting, you have the packet up, except for the error section, which is, separated. You have the packet, and you divide by some big number. And you're better off if you divide it by a, what is it? I forget the name of that, where the number can't be multiplied by anything. It's I forget the word now. But you divide it by that, and then when you get to the other end, you multiply it by it. And you get the data right back, what you got from. The one problem with this is you have the key, and everybody you want to talk to has that key. So they know what you're doing. And maybe they can do something you don't want. Public key is something a group invented. I forget the name of the people who invented it. But in this case, you have a private key. And they find if you divide by that private key and you multiply by a particular public key, you get your text back. And they know the numbers. There's our number theory people. They know the numbers, so they know how this works. So then they develop these public-private keys, and they sell them. And then you can use them for security. I think one of the problems today with our efficiency of computers, there's a relatively small number of these available. And you can sit down and run all of those on a message and then find out which one it is. So they want to hire people that know number theories so they can develop more of these because they need more. In this case, you have the private key. You're the only one that ever sees that. And you give other people the public key. Digital signature actually works. It's almost the same thing. Is you have a private key, but this is a private key for your signature, and then you encrypt it, and that proves it's yours, that you wrote this and sent it. And so at the other end, they can open it up with a public key and see, and that's what you sent. Nobody can mess around. If they mess with it, if they change what you said here, and you get over here, the public key doesn't work, you get nonsense. You put something else in there, so it's a protection for information. We actually made email for the state of Washington, set up email like this. And it's a complicated bunch of things you have to do to send it, and then to receive it. They say, well, you have one of these emails that's digitally signed. And the rigmarole you had to go, it took half an hour to get that opened up again. And there can be other things. You can encrypt this besides digitally signaling it. So the degree of encryption and protection you need can vary. This is somebody's sending something to me. This is my private key, and they use the public key to send it to me. And then I can decrypt it and find out what they're sending. The other direction I send back, I use my private key, and then they can decrypt it with the public key. So there's all kinds of ways of using security. And it seems to, presently we need more security than we have. Okay, this is Unicode, and this is a group of vendors, including Microsoft was big in this, to set aside space for characters beyond just the alphabet. When you add the 8th bit, you'll find a set of ASCII codes that includes a bunch of letters with umlauts and special characters from mostly European languages. But Asian languages have another problem. They have many more characters in their language than we have. They have a different basis for how they set up the language. And so they set this Unicode, instead of just 1 byte, 2 bytes gets us up to 65,000. That can get through the Japanese characters and enough Chinese character to be workable. I've heard that some are doing 3 bits and 4 bits for the Unicode. And then you have, huge number of characters you can choose to be part of this code. And that allows this ability to use other codes besides just Roman, they call it the Romanish characters. Any questions? I don't know how to get this closed. I got to go back to this. Oh no, I didn't want that. There we go. We got that. Okay, let's get to this. Well, this is how you connect to the internet, various processes you use to connect to the internet. And this first one was what I grew up on, and that's the modem connection. This is dial-up modem, and if you ever download a megabyte file, it took all night. You made sure your computer didn't turn itself off and let it roll and wake up in the morning and hope it loaded. And this was, let's put the next one on to show what it is. They call it old analog line. You were connected through analog to the telephone company with this. And that's why you can only get so much, size of message going through. If you had some kind of ISP that you were Roadrunner or something else that were representing you, and you were literally calling them with the old analog line, and then they would provide you with the internet service. At that point, from the telephone company to the ISP, and from the ISP to the internet, it was digital line. There's more capacity there in digital. Later on, we bought cable connections, and they gave you a cable modem. You didn't have to dial up anymore. You're kind of on all the time. That's more like what most of us have at home now. And this, right from the computer, is a digital line. So you get much more capacity. You're connected to the cable company by a cable. They put that out in your yard, and they get rights to put up their little boxes all over so they can connect to you. And it's all digital, so you get more capacity. From you to the internet. I think most people are something like this at home. Yeah, but at work, you generally have some kind of local area network you're hooked up to with your computer. So you're hooked up to the local area network, not necessarily right to the internet. So you can get on the internet rather quickly. And it's transparent. You just say, I want to go on the internet, and you go on the internet. But that actually involves some kind of gateway from the local area network. And this may not be, on your local area network. It may be in another building from your company, and everything's hooked up to that, and that's where they get the gateway. And this is all, I got to punch one more here. That's all digital. Everything's digital all the way along. There's all kinds, since this is a company, there's all kinds of special security you have to put in this gateway. And generally the gateway acts as a proxy. You ask for something through the gateway, and the gateway asks the other end, and the other end doesn't know who you are. So they can't do something malicious. And then it gets back to the gateway, and it tells you what's going on. And I think that kind of setup helped the numbering problem, the IP address numbering problem, because a lot of times when you're on this is a proxy, your computer number is given on the fly. So what your address is, your IP address is given, and it's only temporary while you're working. And so you don't have to have as many addresses. Only the computers that are active need an address at the particular point. Okay, these are modem processes. You have when you're sending signals, you're doing stuff to the signal. The signal is carried on a wave, a very high frequency wave, carries the signal over the higher the frequency, the more information it can send. And in that high frequency waves, there's different ways to make a bit. And this is, I got ahead of myself. This is frequency shift. You see this one in the middle is a different frequency. And you send that frequency shift from your computer, from your system, and the other end, it interprets that frequency shift as a bit. And this is amplitude change. That can affect it. This is all one amplitude, and all of a sudden there's a lower volume, so to speak, and the other end can detect that. I mean, these are small changes because they want to put a lot of these into a signal, but the other end can detect it right away that it happened. And then there's phase shift. To show it, I make it an extreme phase shift. To see what's happening is the phase is here, and all of a sudden there's a totally different phase it's in. And those phase shifts tell that this is a bit. And then, oops, I missed something here. Oh, no, I got this one doesn't do it right. I lost my picture here. Get through quick there. Oh, there's got to be There it is, and combinations. This is, most systems use all of these, and they kind of combine the different ones to say this is a new bit, this is a new bit. So you get you can get more information. You can squeeze the bits closer together by doing it that way. Okay, each change in this signal that's carrying this, each change can be a bit. For each bit, there's two different choices it can be. I got to turn it this way to do it. Okay, and this is just showing, this is a little chart where I show how these are combined. You know, how the bits are when you have one bit, you can be off and on. So it kind of shows how it works, how the coding works. And when you have two bits, you can have four different combinations. You know, this one off and then all on, this one on, off, while this one's off. And I'm over here, I'm relating what these are in the number that they represent. The bits represent a number. This is 0, this is 1, this is 2, this is 3. And then when you have the 3 bits, then you go what the combination you can have. You can have the 8 different combinations. And 4 bits, you get 16. And for 5 bits, you get 32. And this is how they make codes up. When you're setting up a code as a programmer, you say, well, how many different ones I do? That's the number of bits I have to take to keep track of this information. Some basic definitions. Baud is the sampling rate. BPS is the number of bits sent over the line. They're related to each other. Simplex is a way of sending information over a line. This is one direction only. The information can only one direction, and that's sometimes if you're just kind of dumping data, you can send it this way. You're not waiting for a reply or anything like that. And this is half duplex. You can go back and forth between the two sides, which works, but I think most connections now are full duplex, both directions at the same time. Asynchronous, they talk about this in another presentation, but this is where you're just sending one byte, in a sense, one set of codes in a small group and at a time. I mean, they don't do this much. I suppose when you're sending, error messages or something, you do this. But it's just a line of bits, and there's things that say when the bit begins and when the byte begins and the byte ends. And then there's synchronous, and that's when you're using a packet. And they call it synchronous. To use a packet, the two ends have to be synchronized so they know when this packet starts, when you send it, it starts here. When they receive it, they start at the same point. So they're counting the same thing. And this is some of the connectivity types. And this is the type of connectivity you have, analog. They call it a modulator. So you have lines coming in together, is if there are analog lines, then this is what you want to connect the two lines together. If you have analog to digital, you use a codec to connect the two systems. And this is when you go from digital line to an analog, it's a modem. And if you're going digital, you have a digital transmitter. Any questions? This is, I guess that's talking about how the signals are sent. What we will call later is the physical level. Uh-oh. It was on the wrong end. There it is. That's better. Okay. Type of networks. There's all kinds of ways networks are set up which all connect together in making the internet. And one of the things is who owns the network. If you have a network in your company and you're not, I mean, I've had companies that have much of the internet themselves, and then they hire somebody to connect between buildings. One company did their own connection between buildings. Every time you had a storm, it blew out all the computers because they didn't know how to do that protection from electrical storms. But a private network, you own the network. A public networks, it's owned by a telephone company or a communication company. And I picture the telephone wire. They don't necessarily hook cables up this way. They dig holes in the ground and do it that way now. Then there's value-added carriers, and they add value to something somebody else is doing. And this is, these are maps of Washington. When I was a programmer, we had to deal with the different counties in Washington, so I drew up some maps on counties, and I just picked out pieces of the maps here so we could do stuff with this county and then point out the different counties. But this is a wide area network. It's, could be many cities involved. State of Washington, all of their different offices all over the state were on the wide area network. This is metropolitan area. It's the same as the other one, but it's probably within a metropolitan district. And then a local area network, it can be in a building or it can be just one room in the building that's under that LAN. Okay, transmission technology. A dedicated communication line between stations. That's when you called somebody in the olden days, you literally had a wire. It had to be amplified all the way along. If you call somebody in New York, there was a wire connecting you directly to that person. More commonly today, everything is done packet switching. When I was taking the Ph.D., we went down to the telephone company, and they still said some of these, but they were switching entirely to this. And they had these big cables, and they were hooking. This was in the office. They had lots of cables to do this right in the office. And Now it's what they call, it's a laugh, but they call it connectionless connections. You have a connection, but there's no connection. And it's a better word would probably be virtual connection, but this is still what they call it, a connectionless connection. And under these things, particularly when I was in my Ph.D. program, at least one of the students, and I think the others, were working on this frame relay process. And a frame relay is how you send large amount of data between short hops across systems. And this asynchronous transfer mode was what frame relay settled on. And the point is, the packet itself is only 53 bytes. So you had to send a lot of packets. They're not packets, they call them frames, I guess, but they're kind of like packets. You had to send lots of these frames to get a message. But that worked better. The short distance meant they had less clashes in the system. Okay, the virtual circuit network layer resembles the message, reassembles the message as if it came as a whole. When you get to the network layer, these packets are put in little pieces. The whole message is not all in one packet. And so the network layer puts all that together and then hands it to you if it's a message to you. Broadcast routing, you send it just everywhere. The internet is sort of like that, but with addressing, the packet will tend to be focused on where it's particularly going to. Centralized routing, this is what they decided on when we were studying this. They wanted to have this kind of, the routing was chosen. This isn't the one, this is the one. Dynamic routing, the system chose what direction to go. And they always say, like, right now all your messages are going through Chicago, and something happens in Chicago and everything's shut down in Chicago. The internet will automatically go to Atlanta or something and go around it. It'll do it automatically. So it's kind of prevention from emergencies. We're more into the centralized. If Chicago's not there, they can get around, but it's not as easy because all the signals are meant to go to Chicago, so to speak. This was based on the studies. They said that when you centralize, you do the hub and wheel, it's more efficient in some ways. For some things, it's much more efficient for that. And all your airline schedules were done by that rule. And they found, well, it would be more efficient here, but that wasn't what the internet was for. The internet was for always getting your message through, no matter what happened. Any questions? Getting used to this mouse on here. There we go. Okay. Network architecture. This is a picture of the two computers networked with some kind of signaling going between them. This is what I was talking about, asynchronous. I don't know if anybody does this, but if you almost have to just two computers connected together and nobody else, because there's no room for addressing or anything else. But you just take a bunch of bits and send them on the line. And the other side can interpret those. There's a start bit, there's code that tells what this is about, and then there's a parity bit. And there's not a lot of room for a lot of messaging with this. And I suppose when your refrigerator talks to the stove, it might be able to do this, but most of us work with packets. So the packet is the system they decided on, and this is, I mean, they're packets for different purposes, and we'll get into how that works. But the packets have certain set-aside regions that are for certain types of things. And generally, there's 4 different regions. There may be some with some other like 5 or 3, but most of them have 4. And the first is some kind of address issues. And for this layer, it's address issues that play a part in this layer. You know, that in the internet packets, the IP has the main address. That's the address you're going to. But the TCP packet will have something about addressing in it. Then there's some kind of header for the protocol itself. This tells protocol issues. And that's, I don't know, I didn't understand exactly what it is, but I understand why they have to have this. And then you have the data itself. Hopefully that's a large part of the packet, so you're not wasting a lot of time with overhead. And then some kind of error check. And it's the error check for this particular layer. Most people are on Ethernet. That's most companies. And it's not because Ethernet is efficient. It's because Ethernet is extremely easy to manage. It's one of the easiest ones of these to manage and make work right. The computers are all hooked together in the same line. And to prevent clashes, before you send a message, you check if the line is empty. Your software does that. And then when you send the message, there could still be a clash. 2 computers send at the same time. So you have a clash, and they both quit because they know the message isn't going to get through. And then they're given a random number how long they have to wait. So it's less likely they'll start out at the same time again. And this is a chart, and this is why did they go to Ethernet? The efficiency of sending messages. You know, this is the theoretical maximum line speed. You get to a certain point and you don't send any messages. If you're trying to send too many messages on an Ethernet, it won't work. It's dead. 0 messages sent. Well, what happened to this chart is they make the capacity of the line so huge that this is not a problem. That's easier to do than maintain some of the other methodologies. This is a ring. I like these kind of things, but you got to realize when this is, you watch this thing go around, all the computers have to be on and working right, or the whole thing falls apart. That's one part of the management. Besides, one of these computers is kind of managing this ring, this message that's going around, and it has to check for problems and change those, and it has to be fairly intelligent about doing that. So the message just goes around like this, from computer to computer. If you have a message, you put it on, and it's addressed to one of the other computers, and the message comes off when it gets to the other computer. After it comes off, the message can go around, and somebody else can put a message on it. It just goes round and round and round. Simple, but there's complexities with maintaining it. And one thing is all the computers have to be on. But it has a nice curve for usefulness. It gets to the point where it uses almost all its capacity, and doesn't die out. In fact, this up here is you've lost capacity because that's all the message that get through in this cycle. but you're using the line capacity much more efficiently. The token bus is really a ring run by a server. And I'll just show, I just show one of them. But it's kind of like polling. It polls each computer and said, do you have a message? If you have a message, then the major sends it to the next computer. This is really difficult to manage. Because actually you have to have, if something happens to that server, you have to have a spare server and it switches to that. That's one thing you have to have, or the whole network is shut down. But there's other complexities that it's really hard to manage. But it's beautiful because you have that same curve that the ring network has. Now this is what most of you are probably on this at work, something like this. You're on a LAN somewhere in this office, and you're hooked up with a bunch of LANs in other offices, and somewhere there's a switch that you send a message over here, it goes through the switch to that one. All of these are Ethernet, and the backbone is some kind of switch, some kind of router, or set of routers that get you to where you're going. Okay, when you go on the internet, you have an ISP, and then that goes onto the internet. On the internet, there's a bunch of routers all over the place. And computers that are on there act as routers. There are routers that are just routers. I don't know how much I get. So you're connected with all this stuff. And when you're sending out a message, who knows which way it goes? I don't care, just so it gets there efficiently. In a sense, I'm saying the internet is a switch network. The basic process it's running under is Ethernet. Okay, to go into what packets are and how packets work, this is a typical packet that I showed you before. Get that over that way. Now, if you have two protocols, that's a TCP/IP. This is the outer, these are the outer, and this is the inner packet. The inner packet takes the data spot on the outer packet. And it's just in there as data. This packet has no idea what's there, it's just data. And each has its own protocol in the process. And I think I show SNA a couple times. This is the beginning of really networking for computers. And IBM had these big mainframe computers. They cost millions of dollars. And they're very expensive. And so the time on them was really worth a lot. And they needed to find a way to use it to its greatest efficiency. And this was the process they used. Everybody in the company got a terminal. You notice they got the green, and there's a green screen. Green screen terminals. They were unintelligent. Whatever this showed was sent there by the computer. There was nothing in here that could make a message or a picture or a screen. The screen had to be sent from. All that do is just put what the mainframe said put on the screen. But everybody in the company could be working on that computer. If they had apps on the computer, they could kind of log in, go and run their app. They do it by time sharing, and it was sent through this network of system so all this system would work. And IBM, in developing this system, realized the complexity of controlling messages. and they set up the SNA system. We'll talk about that later if we get time. Any questions? Got to set this down. I got to use both fingers here. There we go. Okay. Got to go back up to the top. Whoop, that's what we just saw. I already saw that one. Okay. Okay, the telecommunication architectures. The SNA taught them the layers of stuff they needed to process to make this network system work. And so they developed the 7-layer system. And this is the 7 layers. When I went to my PhD is literally in the internet. And we had, this is like when I was a chemist, you had to be able to produce the periodic chart. Well, you had to produce this and then tell what each layer was. They give you a test and you just write it out, 20 pages, whatever you needed to do. This was the key to knowing how network systems worked. These are the layers. Repeat it again here. Of that system. So this is what our test would be, to write this all out. What's an application layer? And that's, the application layer is the interface between you and the network. You are talking to the application layer. Like you're on the browser, you're talking to the application layer about what you want on the internet. Okay, then the idea of the 7 layers is this application layer is connected to all the layers underneath it, so you get an internet message to work. And what those layers are doing, I mean, you don't see when you're doing the application. I want this website, I want that, I want to read this. You don't see all the other layers. They're supposed to do their jobs transparently and without even being noticed, so to speak. So when a layer is involved with, say, this message, it only deals with its layer. It ignores all the rest. That's not my business. Like I said, when there's a packet as data to the layer that has that packet, the other packet underneath it as data, it's just data. It has no idea what those information is on that inside the data. At the application layer, telnet, file transfer, FTP, those are all at the level of, they're considered to be a level of the application layer. And this is for taking stuff that's coming from the internet, information, data, bits, whatever it is, and making it visible to you so it makes sense to you. It makes sense to you versus making sense to a computer. If you take that data, you want to make sense for a computer, you do different things to it than making sense to a person. And this application layer, they talk about the OSI. That's the rules for making layers. In this case, SNA agrees with what OSI said was the ideal. TCP/IP doesn't, in a sense, have at this layer. That layer is in the browser. The browser does that layer. So I always thought this was a mystery layer. They explain, what's that doing? I got through the Ph.D. anyway. But this actually is formatting the data. The data is coming in different forms, and it's sort of formatting the data itself so the application layer can use it. And this is where compression, encryption, and decryption are handled. These three are actually done in the TCP layer in the internet set. And the idea is we'll see the picture of the two sides of an internet message. The layers are talking to the other side at that layer, and that's all they're talking to. So if you have the presentation layer, in a sense, at the other side, it only, what the presentation layer is doing here is only seen by the presentation layer at the other end. TCP/IP, again, that's not done by TCP/IP. That's kind of the responsibility of the browser. And in a sense, the application, presentation, and session are kind of all put together. And it's not done by the code in the packet. It's done by the browser and then stuff on the server that's sending the message that handles all those together. SNA, the presentation level, is very close to the OSI model. Session is a very important thing if you're programming apps for web use. You'll find the session layer is supposedly taken care of by the system. There are very low amount of session information is handled by the system. And I find when I'm programming, we had people who were filling out forms, and they'd fill out the form, and then they'd go to another screen, and they'd come back, and the form wasn't there. I mean, it's like, so I had to learn so they could use the forms, I had to keep track of where they were on that form in my code, because that's session data, and it doesn't do that for you. It does some session data. When you go on and off, it knows, oh, you're back, and it's the same person. They know that, but they don't know a lot what you did before. And that's sort of the connection is that session. This connectionless connection is a session that you're having between you and the other server that you're working with. It establishes, maintains, and ends the session. .NET was supposed to do more about the session. When you're programming, it keeps more session information. But it didn't keep enough for me. I still had to keep my own session information when I was programming in .NET. But there was less session information I had to keep track of. The session variable is in the state of the session. Like I said, it's minimal under straight HTML. There is some, but it's not enough to do an app with. You can reestablish a session is broken. sometimes. You got to get back quick. Trying to get it to reconnect. Okay, the host computer, the client, talking about the server. The session states it's important. The server has to know those. Because you're only in the session. The server has all kinds of sessions going on. So it has to know which one you are, so to speak. And again, the session, presentation, and application are not part of TCP/IP. The SNA has these kind of split. They don't follow the rules of OSI, and they're sort of similar, but they do a little bit different things. Presentation layer and overlaps with the data flow control layer. Transport layer, we have a transport layer on the TCP/IP. That's the TCP. So it has a lot of little processes it's doing with how the message is getting to one side to another. Not where it's going, but how it's going there. The transport layer is where the message is split up. You have this long 20-page volume you want to send. If it's sent over the internet, it's broken down little bits in the transport layer. When it gets to the other end, it can put them all together where they belong. So it says what you want it to say. It looks like the one that was sent. And when it doesn't, you get, if this gets goofed up in process for some reason or another, you get scrambled eggs. Your screen will be just, it's awful. The multiplexing is done in the transmit. Actually, the encryption and stuff is done at the transport layer. Error checking. That's one of its big responsibilities. It's the main error check. That's part of it. Does the error check. If the packet's no good, it sends back and said we didn't get that packet and asks for another one. So again, the SNA kind of overlaps, data flow control and transmission control later. Network layer, we have a network layer in the internet system, and that's IP. And they said the interface between the carrier and the user, it's the one that addresses it to you, so it's in charge of getting the message to you. And when you send the reply, it's in charge of getting it back to the server. And here, between the layers, the transport layer sends its message to the IP layer. TCP sends the IP, and then IP sends it on. When messages are going the other direction, the IP takes the message from the internet and hands it off to TCP. That just says the same thing. It's going. These are how the layers are talking to each other. SNA calls it path control layer because the important thing is the address, where the packet's going, and the path will try to get to that address. And the routers know a little bit about what the routers on this side are and what the routers on this side so they can get to the right address. Okay, and LAN protocols, the LAN does all the next two layers, the bottom two layers, the data link, and it's all done by the rules of the Ethernet in general. IP address has become the address, everybody's address all over the world. That's your IP address. Your computer hasn't. Now, like I said, on some LANs, you won't have a specific address. You're given an address while you're processing, and that's the save addresses. I don't think they've gone to the 6th layer IP address because they haven't needed it with using that kind of a trick. Data link layer, this fascinated me because I don't think the professors understood exactly what it was. Uh-oh, there's no sound here. Anyway, this is the digital, this is a telephone call, and when you're dialing up a modem, and you get this strange message, and it goes back and forth, buzz, 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 buzz. And that is the data link. You're hearing the data link acknowledge and synchronization. And it's all that noise over the line, and that has to be done. And that's what the data link is all, that's part of what it's about. It does that handshake, and then it controls that connection to the handshake. I'll get into that more. Hope we got time. Establish a connection, maintain a connection, closing connection. That's as contrasted at the higher level you were doing it with a session. This is doing the connection itself. It's controlling the physical level from a software in this system. And in TCP IP, it's handled by others, usually by an Ethernet system. And rather than following the frame relay, they use Ethernet to do that part of it. The LANs actually handle the data link. That's what I'm saying there, layer. And SNA calls this layer the data link control layer. Physical layer, that's just the wire itself is what you're talking about. The signals themselves, the bits, how they're going, how that's getting from one place to another. You know, the strength of signal, the control over the signal, all that kind of stuff. Physical of the the signal itself. Voltage, currents, type of circuits, the duplex or half duplex, and interface standards. Those are, you know, they're kind of basic, more engineering than computer science. This is the speed of bits that are going. You're worried about in the physical level. Up higher, you're wondering about the speed of packets. Here, you're just worried about the bits themselves. In a sense, the physical layer doesn't know this is a packet. It just knows it's a bunch of bits. And each computer is hooked to some kind of wire, and that wire has rules on how you're connected up. Somebody comes in your office, oh, we got a new LAN today. He does a bunch of stuff on your computer. You're hooked up. So this knows nothing about anything but just the bits and where the bits are going. You have to have a physical layer. Somewhere along the line, you have a physical layer. Now, sometimes it isn't a wire anymore. A lot of us on Wi-Fi, and it's a Wi-Fi signal. They don't have to put anything in your computer. They put a Wi-Fi system, a little card in your computer, and then you can talk to some box up on the ceiling. Same thing, but it's still the same process. Okay, here's a bunch of different systems. This is the OSI, you know, as 7 even layers, and here's how SNA kind of overlaps This is, just to get a picture idea, it's not exactly like OSI, although OSI was actually developed from what they knew in SNA. This is the internet. And like I said, the application does these three. Transport is literally the transport here. The IP is the network layer. And then this is done by some kind of network interface like Ethernet. Although transport here may sneak into some of the stuff in the presentation with encryption and other stuff like that. Another picture of it. Just more of the same. This tells some of the software titles that are involved in these different layers. And then, if you ever run Novell, Novell had a way it fit in with this set of rules, more complex. And AppleTalk was another one that handled messaging for you, kind of more complex than the internet. And this is when you're setting up systems, what do you need? So, if you're just a repeater, you only need to go to the physical lever. You're only just sending bits when you're a repeater. It doesn't make any difference what's in the packet. You're just sending the physical layer. If you're in a bridge, you need to get to the data link level. So you have to read the packet as it's coming in to the bridge up to the data link level. And with a router, you need the address, and that's in the IP layer, the network layer. So you have to read the packet to that point. And a lot of your security systems, they look for things up to that layer. When you're routing, they'll check up to the network layer to see whether there's a problem with this packet, and we throw it out. Because a lot of your stuff that comes as problematic, they're poorly formed packets, and it'll show up in the network layer. Any questions? That was the basis of our Ph.D. program, that we had to understand that. But understanding it fully, you really know the internet and what's going on the internet. Let's show this one. Oh, no. Trouble with this, getting it to do what I want it to do. I'm used to a different kind of mouse. There we go. I'll just show you the frame relay. And this would have sound in it normally, but I guess the sound isn't available to me. So we'll go with this. There we go. Okay. If you don't have an Ethernet, and big companies have a lot of information, they're not going to mess around the internet. They're going to take the information and send it along to the next company through some kind of frame relay process. Especially in a large amount of data, this seems to work better than going through the other protocol. Okay. Without internet, you have to have a data link layer and some kind of frame to handle the process. And then when you do this, that layer, the data link layer, handles a handshake. That's what I said, when you send a fax and they do this dial-up and you hear the sound of them doing this, the doop, 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 doop. That's the handshake for doing a fax. And it's done on I guess it's at this level, the data link layer. Okay, this is the data link handshake. And that's a repeat of what I already said before. I got to turn this way. Oh, there it goes. This sync, ACK, and ACK. Oh, I went too far now. I don't know if I can go back. There, go back there. I pushed too many buttons. There we go. So, and this is when the noise, each one of these, there's a beep or some kind of noise in that when they're doing the fax that tells it that's happening. And then after this, then their application data can go back and forth between the two connections. And that's, I think that'll help you understand what this data link layer is. And the fact is, in most cases, you don't need it because Ethernet does this differently. It does it by that process of trying to send a message, and if they clash, then giving a random number when you start over. Yeah, and the thing is that the frames are very small, and they felt that was more efficient so they don't clash with each other. But then you have to send an awful lot of frames to get any kind of message. There, I've looked up what a frame packet looked like, and actually there's 4 different sections on this, and the message is here. And there's some kind of error check here. I don't know if you know lorem ipsum. When you're testing a text, a text system, and you're trying to see how it works, they have this on the computer. You can download lorem ipsum. It's this whole speech by some person way back, all in Latin, so it doesn't make any sense to anybody. You're not trying to make sense. You're trying to fill space to get a message that you can play with and see what it works like. Getting close to the end here. And if you have another frame, it looks the same, but it's further along in the ipsum lorem data. Any questions? Okay, I should show this one for sure. So I can get this mouse to work right. There we go, okay. This is kind of short. Well, yeah, relatively short. Okay, internet packets. And there's the TCP packet, and I have ipsum lorem on here as my message. I don't know if you can put that much of ipsum lorem on a packet, but something like that. Ipsum lorem is 20 pages long, so you can make your message as long as you want to. But this is TCP, and the information is put in the TCP packet from the browser. It goes to TCP packet. And then it goes to the IP level, and the IP wraps that packet in its protocol. And then this can be sent all over the place, all over the world, whatever. And this is what happens. The message is broken up into TCP packets. The packets are sent to IP, and they're sent around, and then it rebuilds the message from the same 4 packets here, and then you got the message. Anyway, I'll try to just do it again. There we go. I've hit the button too many times and it went on beyond what I was supposed to do. That's the way the internet works. And wrapping the packets and sending it around in a circle. And down here, this is probably some kind of IP or Ethernet system that carries it around. That's real short and sweet. Yeah, that's the one. Okay, this is how you connect between 2 systems. This is my computer, the client, and this green thing, that's the browser. The browser's doing my talking to the internet. This is some kind of web server that we want to connect up with one way or another. This is a page on this web server. This is the page we want. It's on a disk somewhere on the web server. So the browser says, you tell the browser, I want this page. The browser sends that over the line in some kind of I want this page. You get there, and that's the page you want. The server just, in a sense, if this is just HTML, it just sends it. No intelligence needed here. And you get it on your browser, and it shows up in your browser. The browser interprets that page. The page is in HTML and interprets it. Okay, now if you're going to do, this is, when you get here and the page is showing up, it does some tricky things for you, whether you want it or not. It saves the cache of that. And I believe that's to the disk, puts that on the disk. So if something happens, you go back to the page real quick. But if you go back to the page and you hope to get a new copy, what's that?
A few more minutes.
Okay, a few more minutes. Okay. When you go back to the page, it'll use the cache. And that's if you're looking for changes on the page. Say you're looking for a stock market report, and it's supposed to change, and it uses the cache. That's 10 minutes ago, because it's using the cache. There's also a history that's kind of kept by the browser in main memory, and that's another copy. That's the copy that came. If you make changes to a page, that the copy of the page, I think that's the history is a copy that came, and the cache is, when you make changes, it goes back into the cache. Anyway, the two are different. If you go to the history and you go to the cache, and you get different results. All right, now we're going to use something where we're going to get some information from a database from the server. And I'm going to show you how this works so you understand the security system for it. Okay, either a post or a get, you're going to ask for data from the other, not just a web page, but data. This is not an HTML page. So the server has to do some processing, then more process just dumping it. Well, one of the things is you ask for something out of the database, it has to go onto the database server. So this process can call the database server. You notice you cannot call the database server from here. That's a security process. And here, the web server can call the data process. That's a security level. So the data comes back, and then this ASP program that's now running in the server does things with that data. It puts that data into the web page, does some other fancy stuff, and then sends it down with HTML to your computer. And then you have a web page. That's all you have at this end. You don't know what went into that, but in it is data from the database. Say the stock market report. And again, you do the caching of that page. Any questions?
I want to thank you.
Okay,
for the
okay.
presentation. On behalf of AFCEA International and AFCEA, I'd like to present you with this coin and our lei. Thank you, sir.
Oh, thank you.